All right. Our final presentation for today, it comes from Maciej, Cytowski, and Mariam, Ahtar. Maciej comes from POSI, and Mariam comes from Quantum Brilliance. They're going to be discussing the challenges of deploying the QB system in an HPC facility. Maciej,
thank you so much. Yeah, thank you so much, Brian. I hope you can hear me all.
I can.
Let me share the presentation. Hopefully you should see the slides.
I do.
Cool. So let me start. So hello, everyone. My name is Maciej Cytowski. I'm from POSI Supercomputing Center. At the beginning, I just wanted to acknowledge the traditional owners of the lands we are connecting from today, and pay our respect to their elders, past, present, and emerging. This talk will be giving you an overview of challenges of deploying a quantum system in a supercomputing facility, basically right next to a supercomputer in a POSI Supercomputing Center. This talk will give you a little bit of details of the close collaboration we have engaged into with Quantum Brilliance. So it's a joint talk, and it's my great pleasure to have Dr. Mariam Ahtar today with me. Mariam, over to you.
Hi. I'm just going to request control.
Yep.
Thank you very much. So my name is Mariam Ahtar. I am here from Quantum Brilliance and can't quite change the slide over. Thank you. Hi. So yeah, I'm one of the researchers of Quantum Brilliance, and Quantum Brilliance is a leading diamond-based quantum computing company. So what that means is that we actually leverage the properties of diamonds within our quantum processors in order to be able to build devices that we can then interface with classical networks. So we are a small company. We have about 80 staff across 5 other offices. We have offices in both Australia and in Germany. And our sort of vision of what we would like to deploy is these compact quantum processors, which we can then install into either data centers for massively parallelized quantum computing networks, or actually also in edge cases. Because of the properties that we're using in Diamond, a lot of the extra things that a quantum computer might need that makes it really sort of cumbersome and bulky to deploy, things like big vacuum chambers or cryogenic cooling, we don't actually have that applicable to our technology. And so we can see that our diamond-based quantum processors can actually have a wide range of applications, particularly also in edge cases where a small number of qubits can actually have a rather large impact. And we're also a full stack company. So we not only do our hardware, but we have a full stack software as well. So that's a bit about Quantum Brilliance, but I'll pass it back to Maciej to introduce POSI a bit more.
Thanks, Mariam. I guess you'll probably hear about POSI throughout the conference a couple of times, but just a very brief introduction. So POSI is a national supercomputing facility headquartered in Perth, Western Australia, on Whadjuk country. We have been launched as POSI in 2014, and we are a unincorporated joint venture of for Western Australia universities and CSIRO with funding from federal and state government. We have strong links, and we have a critical infrastructure and host a critical infrastructure for Square Kilometre Array, so SKA project, which is located around 800 kilometers north of Perth. And we do support radio astronomy operations on our systems, both on data and compute side. It's quite an important moment for POSI, and not only because of the recent deployments related to the quantum computing, which we'll be covering in that talk, but also in relation to the capital refresh grant that we have recently received from Australian government, which allows us to refresh all the compute data, clouds, and visualization infrastructure that is hosted at POSI. POSI is an organization of around 60 plus staff. We are employed through CSRO as our lead agent. Yeah, so one of the biggest components of the Capital Refresh project is Cytowski, is our new supercomputer that you can see here on the photo and also in my background. So Cytowski, its name is actually, it's named after WA, so Western Australia's iconic quokka, so a very, very cute marsupial. It's currently being installed. It's actually, the deployment of Cytowski is actually planned in 2 phases. Phase 1 is already available for researchers since June this year. And phase 2, which will host most of the GPU compute plus additional CPU compute, will be very, very soon available to all Australian researchers. And once it's finally deployed, we will see a 30x increase in compute resources compared to our current, previous infrastructure. So Magnus and Galaxy, that was hosted, 2 systems that were hosted at POSI. But what we usually want to mention on that occasion is also that all that investment that we are making in changing the infrastructure and also looking at hosting such a big system with a great density within a single rack, it also allows us to deploy the system, which is very energy efficient. So we are increasing the compute capacity by 30x. But we also reduce the or increase its energy efficiency by 10 times, which is great. Meaning that your science will be more energy efficient, and also that any flop that will be or any computation that will be run on the system will be using less VATs and will be basically more energy efficient. We have developed strong links with international organizations over the time, and also national ones. Here are our national partners, so all the major universities in Australia, but also the other national supercomputing facility located in Canberra, which we work closely on multiple projects, and our partners from WA, and also our government partners from Western Australia and from other states in Australia. Within our international collaborations, we develop links to major supercomputing centers around the world, but also we develop collaborations with technology leaders. And just recently, that was also within the quantum computing space with Quantum Brilliance and other organizations around the world. And sharing those experiences with other centers is something that we really enjoy to do, because it gives us a possibility. And most of the centers actually are currently around the world are looking already and deploying some of the quantum hardware and their premises. So sharing those experiences around is actually quite important. We actually believe that POSI is a great place. And when we met with Quantum Brilliance around 2.5 years ago, when we started that project, we have identified that POSI, Australia, might be a great place to actually build like quantum supercomputing innovation hub. And that's because of Cytowski. So the system that will become the biggest supercomputer in the Southern Hemisphere. And because of the collaboration with Quantum Brilliance, where you will hear some of the more details from Mariam, but the biggest benefit of deploying that particular infrastructure is that it can operate in room temperature, which means that we can basically install it right next to the supercomputer and basically hook it up with a supercomputer by just making it sit right next to it, operate in the same environment, room, being integrated in Slurm queuing system, so that you can basically submit a job that will use a quantum accelerator. But also the fact that we have developed so many collaborations around the world and inside Australia allows us to connect those wins that we have in the new technology space with researchers that are using POSI infrastructure. And this is the biggest benefit, I would say, for Australia that we have from this particular collaboration, because everything that we do at POSI is then being translated to those new services or maybe trial services that are being available for researchers. POSI also is quite a unique place if you look at the people and skills area, because most of the POSI staff has some research background. So we currently, within that collaboration with Quantum Brilliance, we just to give you an idea, we also have a few of our staff working on developing a code, quantum chemistry code, that will be using this particular infrastructure in a hybrid mode. So running on the supercomputer, but using a quantum device as an accelerator. And this is part, of the new collaboration models that we are trying to build. We have also engaged our training and education department to basically build the program for quantum computing education and outreach, including STEM education as well. But let me just give you some of the overview of things that we did so far. So if you look at some of the updates from last few years that we've been able to achieve around quantum computing, it was, of course, the collaboration with Quantum Brilliance, which led us to the first hardware installation at POSI, and the integration and testing the integration with a supercomputer that we will be hosting at POSI. We also engaged with researchers instead of in form of making sure that they will be able to access these resources. So we have worked closely with Quantum Brilliance to see how those tools can be then made available, how this hardware can be then made available for researchers, and that's both from the cloud computing platform as well as a supercomputer. We have built something that we call the Quantum Pioneers program, where we are working closely with 2 industry and 2 university partners that already have access to a quantum emulator on our systems, but in future we'll be able to use the QDK, so the system that we have deployed at POSI. And education and training activities. This is something that within that space we are currently mostly engaging with University of Western Australia, where we develop a strong collaboration with the team of Professor Jingbo Wang, and we have supported the team there and are working closely with the team there. We have deployed the first Australia's education quantum computer on their premises, which is a slightly different hardware, but allows students to interact with quantum computing. And building on top of that, we are also developing our internship program, where each year the quantum computing component of the internship program actually is bigger and bigger. I think for the last few years it was reaching around 30% of the of projects and students that were engaged in that the POSI internships. Here's just an overview of the collaboration with Quantum Brilliance that we have developed over those 2.5 years. So it started with some kind of like a community building exercises, which at that time when we started had to be organized online. So we started with 2 quantum online seminars, which, by the way, became I think at the time, the most popular online events that POSI has ever run, with more than 200 participants. And so we are looking at why we should be looking at quantum, and how quantum connects to some of the industry applications. We have then built the Quantum Pioneers program, where we're giving researchers and industry access to a Quantum Brilliance emulator on our cloud infrastructure. And then we are sharing our experiences about that during FC Asia conference, and then later also during within our paper for the IEEE Quantum Week workshop. I mentioned POSI internships. That's getting more and more visibility also from the point of view of quantum computing, and also students are asking about how they can engage within that program, specifically looking at quantum computing. And again, collaboration with UWA is working extremely well in that part. We have deployed the quantum computer in UWA, which is an educational system that I mentioned. And in May 2022, we had this very important milestone where we hosted the team from Quantum Brilliance at POSI in Perth for the installation of the first room temperature on-premises quantum computer in a supercomputing center. So this is, you will see some of the photos that Mariam will be sharing, but this is literally sitting right next to the supercomputer currently in the white space here at POSI. There are a couple of new projects that we are working on closely with Quantum Brilliance, and that you will see some results and publications very, very soon. One of that is actually, sharing the collaboration between a supercomputing center and a quantum computing technology company allows us to, share the experiences. And one of that is actually all the experience that POSI has, with deploying supercomputers and making sure that you can submit a job to a queuing system, and how to, hook that up with a specific accelerator, whether it's a GPU or a quantum accelerator. So this is a little bit of an expertise that we have that we can bring and basically make the help Quantum Brilliance team to make the final product ready for basically being deployed in any supercomputing center, but also on the side of the monitoring, right? Whether you were using Grafana or other tools for monitoring the state of your systems, that should also apply to quantum computers. So we are learning together on how we can get those monitoring aspects from a quantum computer and make it, integrated with some of the technology standards here as well. So that's quite an exciting part of the collaboration. Some of my colleagues are working closely with software developers from Quantum Brilliance on the first demonstration that will be running on the system. That will be a hybrid supercomputing, so classical computing and quantum computing application from the domain of quantum chemistry. And at the end, after the demonstration actually will close. A big part of the project will be able to show that the system is fully integrated with a supercomputing environment on various levels, as I mentioned, and we'll have a demonstration of a simulation running on supercomputer and QPU. Then the researchers will finally have access to this infrastructure, so that they can also leverage it for their specific purpose and their specific algorithms. Mariam, I will now pass over to you.
Thank you very much. So from a Quantum Brilliance perspective, quantum tech in general is still very much in its development phase, where some of the biggest challenges in translating the technology comes from just moving from an academic laboratory and making it into a product that is sort of commercially relevant. And that's why our partnership with POSI has been so invaluable, because not only are we enabled to do this translation from a benchtop experiment to a product, but, as Maciej was describing, we get that sort of customer feedback, which lets us tailor, the deployment of our quantum processor to meet these sort of end user requirements. And see on the right here, you can see some of the pictures. That was our first deployment of our quantum processor, which was into the POSI Supercomputing Center. And, we learned a lot from this experience. And so one of the things...
Sorry, Mariam, you just probably need to tell me to switch the slide. I unfortunately, I cannot pass the control over to you. Sorry for that addition.
No worries, that's fine. Let's move straight on. So why would we want to actually put a quantum processor into a supercomputing center? Well, I wanted to talk a little bit about an example of how Quantum Brilliance and POSI are working together on a current project. And for this, we have our client, which is the Australian government, and we have Quantum Brilliance and Trellis Data working as contractors and using the POSI Supercomputing Center to support the development of what is a quantum decoder. So what is that? If we move to the next slide. So the challenge for us was one of signal processing. So here we have Trellis Data, who uses basically a neural network that takes some signal, and that this could be a video, audio, some sort of data signal that they then process through this neural network to get a set of probabilities. And what they want to be able to do is to predict the correct sequence. So what is the most likely sequence of events that happened? And this is actually a very computationally intensive process, particularly if you want to be able to deploy this kind of capability in an edge application where there might be significant resource constraints. And that's where a quantum decoder can become extremely valuable and very powerful, because you can take into account all possible sequences and get a likely result in a very short amount of time. And so this is kind of one of the examples where, you know, a quantum processor can be extremely useful in an edge example. But in order to be able to really realize, you know, what kind of quantum decoder, of what size and what fidelities, and to really characterize what the sort of parameters are associated with that, we then need to be able to emulate a quantum system that can handle these kinds of problems. And that's where the large supercomputing power of Palsy can really be leveraged. So, you know, this is kind of one of the projects that we're currently working on with Trellis Data and with Palsy. And so let's take a little bit more of a look at what we're actually deploying. So one of the things is an emulator. And so that brings us nicely to our software development kit. So as Quantum Brilliance, we don't only do hardware, as I mentioned at the start of the talk, we also do a full stack software. So this software development kit at the highest level basically allows you to run your programs on a classical and quantum system, and you can deploy a hybrid program. At top level, you have your C++ or Python, and then you implement the programming of the quantum system in a kernel on one of the existing quantum languages, in addition to a whole bunch of subroutines that we've already developed, which is the sort of quantum application line. And then if you go a little bit deeper, you then get to the software development kit itself. So this is a sort of public, open source, free part of it that sort of gets shipped out with sort of example applications that sort of use this framework. And invokes the compiler that compiles the sort of quantum kernel together with the classical program, and then translates that down to whatever intermediate representation. And from there, you then have to choose where it targets. So, you know, in one instance, that could be the sort of quantum processing unit, which would be your sort of quantum hardware, like our Diamond quantum accelerator. Or on the other hand, it could be a simulator, or in fact, it could be an emulator. And that emulator part actually has a sort of full set of noise models associated, circuit optimization and placement routines for our hardware. So you can do things like work out exactly how many qubits you'll need for your particular application, and also perhaps what year it would then be available from a hardware perspective, given our roadmap. And so it could be a really useful and powerful development tool to then say what sort of algorithms are possible now and when they are possible in the future. So that's our software. And then moving on to our hardware. Oh, not yet. And sorry, just wanted to also flag up real quickly that when we actually developed our software kit and shipped off and deployed in Palsy, because we were able to put this architecture in place, it meant that from day one, through the Palsy network, we could already communicate with our quantum device and start running some of the basic routines that we needed on our quantum processor. And now onto the hardware. So that's the software that we built and developed. And what about the hardware side of things? So again, we're back to these pictures of us deploying in Palsy. And what we actually delivered in terms of hardware was a 19-inch rack-mounted device. It was 6U, had 2 qubits. and room temperature operation. So no cryogenics or additional cooling that are outside of our 6U device. And it was about 150 watts of power consumption as well. However, the environment to which we then had to deploy that into was the supercomputing data center. And this is from what is a very quiet environment of our optics lab that we initially build these devices. And so these are temperature controlled. They're on optical benches that have this great vibration isolation. We then have come to our data center, which to a little QDK is actually quite a hostile environment. It's loud, there's acoustic vibration, there's airflow, there's mechanical vibration, there are temperature fluctuations. And so we've had to work closely with Palsy, just to characterize and establish what these environmental factors are before we can then go back and think about how to mitigate for them. So this was actually quite a big development process for us in order to really figure out where it is that we need to be able to validate the performance of a device for. And that has led us to actually develop a lot of our own routines in-house, for example, for environmental testing procedures, and to actually have the facility to be able to characterize a device to the extent that we need to in order to be able to implement it in an environment such as the data center. And of course, since our redeployment, we've come back and had to improve and redesign how we build these devices in order to make them far more robust. And that has been an excellent learning curve that Palsy has really supported. And also we're currently working on integrating the monitoring system to the Palsy network more closely so that the diagnostics are just more readily available to the supercomputing center as well. And thank you very much. If there's any questions, we'd be happy to take them.
I currently don't have any questions in the queue. I do have Pat Scott here too on the panel, so to be able to help answer. Let's see. Let's give it just a moment. Just remember, you can ask a question either through the chat panel or the Q&A panel at the bottom of your screen.
Yes, as we are waiting out, sorry, Mariam, I don't think I did a good job in driving the slides. We literally did a coin flip before the session to decide who will do that, but I'm not sure if I did all good. Yeah.
I didn't notice a thing. Mark threw on his camera. Mark, do you have a question?
I did. Well, it's more again an endorsement of a great presentation, and thanks to Mariam and Maciej. I'm just reacting. I'm putting this little character up in here in reaction to the hostile environment statement. We are not hostile here at Palsy. We are collaborative, and we're open to partnerships. No, not really. I did react to that. So we're named after, obviously, the scientific name of the quokka is the Cytownics, which is why we've named our system that way. But some really great insights into how we've worked together and what we've learned from working with Quantum Brilliance. And so it was a fantastic presentation. And I know entirely the context in which you meant that statement, but just thought I'd offer that. Thanks.
Thank you, Mark. We do have one question that came in. It's how is cybersecurity being taken into account with deploying quantum accelerators and systems? Okay,
I guess that question might have many different. Yeah, you can answer these questions on many different layers, I guess, because there might be a question, about, password cracking, things like that, right? But I guess from our perspective, from the perspective of, making sure that this device is being well integrated with a supercomputer, we are looking at, how you can access, who can actually access the device itself, right? So what kind of operating systems are running on the controllers of the device, and whether a user has access to the device, can log into the device itself or not. So from user perspective, researchers that will be using Cytonic supercomputer will be actually interacting with the device by using software developed by Quantum Brilliance. So they won't have like let's say login access to that or access to the device itself. So they will be able to call whether it's C, C++, or Python high-level type of programming languages, library calls to actually use some of the algorithms and schedule some quantum circuits on the device. So this is probably something that we were at POSI a little bit concerned and looking at closer with the Quantum Brilliance. I don't know, Mariam, if you want to add anything to that.
No, unless Pat wants to add anything from the software side.
There's not really a lot more to add to what Maciej said. I mean, in the longer term, we will need to think about low-level things about like preventing code injection and stuff like that. But for now, it's mostly about managing access in a secure way, which is Maciej pretty much covered.
Yeah.
Okay, thank you. That's the only question that I have in front of me right now. Well, I think that was it. So, Maciej and Mariam, thank you very much for the presentation.